Hello student, this is Nitin Chauhan and I am assistant professor of mathematics in engineering department, and today we are starting Euler's equation. Okay, Euler's equation, and this is a topic of calculus of variation. Got it? And Euler's equation, first of all I'll give you the statement. I'll give you the statement of Euler's equation, what states Euler's equation, and after that we are going to do the proof. Okay, so the statement is a necessary condition for I equals to integration x1 to x2 f of x y y dash. This is functional. Okay, this is a functional. I equals to integration x1 to x2 f of x y y dash to be an extremum, is that del f upon del y minus d by dx del f upon del y dash, this equals to 0. Okay, this is a statement of Euler's equation, a necessary condition for I equals to integration x1 to x2 f of x y y dash dx to be an extremum is that del f upon del y minus d upon dx del f upon del y dash equals to 0. This is a statement. Okay, and we are going to prove this. How? We start the proof. Okay, so here, okay, let y equals to yx, be the curve joining the points A x1 y1 and B x2 y2. Okay, these are the 2 points in which this curve is joining these 2 points. Okay, which makes I an extremum. Okay, let y equals to yx plus eta neta x. Okay, this is marked equation 1 and is a neighboring curve, joining these points so that A neta x1 equals to 0 and at B neta x2 equals to 0, and this mark it equation number 2. Okay, these are the 2 points in which neta x1 equals to 0 and neta x2 equals to 0. Okay, now the value of I along equation 1. Okay, equation 1 is I equals to integration x1 to x2 f of x yx plus eta neta x comma y dash x plus eta neta dash x dx. Okay, and we mark it, we are not marking this equation. Okay, when we put the point, then we have y equals to yx plus eta neta x. We're putting that value. Okay, we're putting that value in the functional. Okay, when we putting this value in the functional, we got this equation. Okay, this being a function of epsilon, this being a function of epsilon is a maximum or minimum, is a maximum or minimum, for epsilon equals to 0 when when di upon d epsilon equals to 0 at epsilon equals to 0, and we mark it as equation number 3. Okay, this is the condition of, as you know that this is the condition of maximum minima, when di upon d epsilon equals to 0 to it equals to 0, we have the minima of that value. Okay, so we remove this one. Okay, students, and after that differentiating, okay, we are differentiating I under the integral sign, differentiating I under the integral sign by Leibniz rule. Okay, Lebnitz, Leibniz rule. Okay, this is a rule, Leibniz rule. And what we have in Leibniz rule, di upon d epsilon equals to integration x1 to x2 del f upon del x upon del epsilon, okay, plus del f upon del y upon del epsilon plus del f upon del y dash upon del epsilon, okay, and here dx, okay, and we mark it as equation number 4. So we have equation of 1, 2 and 3, and this one is 4. Okay, we are just differentiating it by the chain rule. Okay, when we differentiate f with respect to epsilon, it is not going to be directly, okay, it is going to be by chain rule. So del f upon del x upon del epsilon, del f upon del y upon del epsilon, and del f upon del y dash and del y dash upon del epsilon. Okay, now but this epsilon being independent of x, okay, this epsilon is independent of x, so del x upon del epsilon is equals to 0. Also from equation 1, okay, what is equation 1? जो neta x1 equals to 0 and neta x2 equals to 0. Okay, so here del y upon del epsilon, oh sorry, that this is equation is y equals to yx plus epsilon neta x. Okay, del, when we differentiate with respect to epsilon, so what we have, del y upon del epsilon equals to neta x, and del y dash upon del epsilon equals to neta dash x. Okay, we have these three equations. We put these equations in this equation. Okay, when we substituting these values in equation, and what it becomes, let me write. Okay, when we putting all these values in the equation, what we have, students, di upon d epsilon equals to 0, sorry, di upon d epsilon equals to integration x1 to x2 integration del f upon del epsilon, sorry, del f upon del y neta x, okay, plus del f upon del y dash neta dash x. Okay, and here we have dx. Okay, now what we are going to do, we integrating this second part, by the by part integration. Okay, So what it becomes? Di upon d epsilon equals to integration x1 to x2 del f upon del y neta x dx. Okay, we keep this remain as it is. Okay, plus now what we integrating it by part. So del f upon del y dash as it is, and the integration cancel out this differentiation. So we only have neta x from the point x1 to x2 minus integration x1 to x2 minus integration x1 to x2 d by dx of del f upon del f upon sorry, del f upon del y dash neta x dx. Okay, we have this equation, and after that what we have? Integration x1 to x2, and actually this points we have neta x1 and neta x2 are 0. Okay, for this complete equation goes to 0. This complete equation cancel out to 0. Okay, so what we have? We only have this part and this part. So I am writing this equation integration del f upon del y minus sign, this minus sign, d by dx del f upon del y dash. Okay, del f upon del y dash, and outside this neta x dx. Okay, students. Now what do we have? I am removing this one. After that, since this has to be 0, only this integration only this has to integration this has to be 0 only di upon d epsilon equals to 0. So for this integration, this is the di upon d epsilon, and this needs to be 0 only when this part equals to 0. So we have del f upon del y minus d by dx of del f upon del y dash equals to 0, and this is known as those students Euler's equation. Okay, this we have Euler's equation. So what we have discussed? We have discussed the Euler's equation, and this is the proof of the Euler's equation, and we have this one. Okay, after that I am giving you some short forms of Euler's equation, solutions of Euler's equation. Okay, what we have solutions? First part is when f is independent of x. Okay, when f is independent of x, what we have? We have del f upon del x is equals to 0, and Euler's equation becomes, what becomes Euler's equation? D by dx f minus y dash del f upon del y dash equals to 0, and on integrating, when we integrate it now, on integrating, what we have? F minus y dash del f upon del y dash equals to some constant. Okay, okay, so this is a part, this is a form of Euler's equation. When we have a function which is independent of x, we can solve it directly by this one. We no need to solve the complete Euler's equation, students. Okay, so now we are moving to the second part. Second part means that second. What is this second? When f is independent of, when f is independent of y. Okay, when f is independent of y, what is becomes del f upon del y equals to 0. Del f upon del y equals to 0 when f is independent of y. So what we have Euler's equation, what? Del f upon del y minus d by dx del f upon del y dash equals to 0. Okay, so when this is equals to 0, then we have minus d by dx del f upon del y dash equals to 0. Okay, on integrating, when we integrate it, what we have, I am writing here on integrating. Okay, when we integrate it, what we have, del f upon del y dash equals to some constant. Okay, and on integrating it, we have the solution of what we are looking for. Okay, so this is second. And what is third one, students? Third one is when f is independent of y dash. Okay, when f is first is independent of x, second is independent of y, and third one is independent of y dash. So what we have, then here del f upon del y dash equals to 0. Then Euler's equation, what we have, del f upon del y minus d by dx del f upon del y dash equals to 0. Ab del f upon del y dash equals to 0, so then this part cancel out. So what we have, del f upon del y equals to 0. Okay, and after that when we integrate it, okay, when we integrate it, we have the solution of what we are looking for. Okay, this is all about Euler's equation, students. In the next class we are introducing some of examples in which you can easily understand how these equations are going to be used and how they are useful, and by what we can easily solve the Euler's equation. So this is Nitin Chauhan. Thank you, students.